Hello, everybody. My name is Elena Beretta, and I am assistant professor at Vrije Universiteit Amsterdam. My work mainly lies on ethical AI and human-AI interaction. So I would like to start with a quick metaphor. Uh, Imagine a mosaic artist that is arranging tiny glass pieces into a masterpiece, and each fragment forms along is meaningless, but together they form a complete image. So vision transformer actually works in the same similar way. So they simultaneously grasp the bigger picture that rather than isolated details. So I think that something that is worth to mention is that vision transformer has revolutionized AI in 2017. And then they have been introduced in computer vision. And this process of capturing images has revolutionized, and it is revolutionized a lot of AI domain. So for example, from medical imaging, enhancing diagnosis, in self-driving cars, in security systems, and of course in general purpose generative AI application. So what I think is important is the question, what makes these models so different from earlier AI models? So I think that to explain this, I try to do with a quick metaphor. So imagine you are in a meeting with 10 people discussing an important topic, right? So no matter if you don't know each of the model that I'm citing. So for example, with the recurrent neural network, you have sequential listening, right? So you listen each person, but you understand what you have been told when you have listened the 10th person, okay? With convolutional neural networks, you don't listen to conversations sequentially, but you group people and you focus on little groups, small groups, based on proximity. And the last one, you have the vision transformer. So with the vision transformer, the key idea is that everyone speaks at once, right? So somehow you understand everything and you can focus on what's important, okay, without losing any information. So the strength is what we call self-attention mechanism, okay? So because it captures both local and global relationship in the conversation instantly. And I think there are some two main reasons why we have to study vision transformers now, because they are revolutionizing AI domain, and because we already know that deep learning has been, is biased for certain groups, and vision transformers are now in an evolving domain. And the other one is a more domain specific, and the fact that detecting bias in images is a bit more harder with respect to text, right? It's more contextual. So imagine, for example, a CEO in a hoodie, right? It's formal or is informal. So the interpretation of bias in image is heavily context dependent. So the question that we try to answer with this work is how different VIT models encode and propagate social biases. For answer this, we evaluate 10 pre-trained vision transformer, and we try to understand which layers of the transformer encode bias. So for example, in the early layer or in later decision-making layer. We wanted to evaluate how different training strategies influence bias, so for example, generative or discriminative training, and how bias propagate within bits. Okay, so how the bias has been encoded at the beginning in the early layer, and how this information propagates to the layer of different models. So this is a general pipeline of the model. And we use this test that is called IEAT that I explain now. This test is a test that has been borrowed by cognitive AI, I would say, no, sorry, cognitive psychology, and that's been adapted to computer vision task, right? So this means that it takes into consideration association. So it does not require classification, but instead it examines how the models internally organize social concepts, in their embedding space, okay? So the test quantifies how closely a model associates target categories with specific attributes, okay? So for example, gender and career, okay? One key limitation of this test is that it's binary, and I consider it one of the major limitations of this test. But for our purposes it's a beginning, okay, to study how vision transformer works. As I said, the idea is to study the association. So we select two target categories, and these categories are represented in these images, right? So we extract embeddings from the pre-trained vision transformer, and instead of asking the models to classify the image, we extract its internal representation, so the embedding, from the last hidden layer. And we did this because embeddings contain information of the image. So we didn't want to study classification, but how the information passed to the last layer. And at the end, we measure how close the embeddings of target images are to embeddings of the attribute images, right? And we did so by some measure using, for example, cosine similarities, and these tell us how the distances and how strong is the association, okay? So a stronger association, for example, suggests a higher level of bias in how the model structures social categories. Some results. Of course, the bias trends are different across different models. Something that is worth to mention is that is persistent in all models, but this depends on the architecture and also the training paradigm. So some models, for example, amplify bias in their representation, okay, while others show weaker effects. Something that I think it's important to mention, especially for our study, is that discriminative and self-supervised models tend to amplify dataset bias. So, and this is true especially for the logit embeddings. So the stage where models make the final decision. This means that if the training data contains stereotypes, these models reinforce and even magnify those biases in their internal representation. In this we have some graph, but we have more in the paper. So, similar trend is shown for gender career bias in the IT. So bias tends to be amplified in the later layers. And female representation are more strongly associated with family-related concepts. I think that for what concerns this kind of bias, so some models amplify stereotypic association clustering, especially for what concerns gender and size, and bias is observed both in internal feature representation and final decision layer. So I concluded with some takeaways. The first one is that the training objective determines bias magnitude, and this is quite important for understanding vision transformer. Discriminative and self-contrastive model amplify bias. The logit embeddings form much tighter clusters, and so these exhibit much higher bias. Generative models in such a way diffuse the bias in the more scattered layer. And the last one is that association tests show certain demographic intersectional bias, especially for association related to gender and ethnicity. Thank you.